Today we will discuss Eddie-Hofstad equation and Hainsworth equation. Right, last time we were having an issue with low substrate concentration, that it was giving Vmax, which is not expected, right? So how we came up with this equation, that is the thing. Now, right, as you will see that how am I solving that? This will go, right, not an issue. Now let's divide it by substrate. You will get V naught Vmax minus Km V naught by S. So this is the equation that you get. And this one is something which is important to understand. This V naught, this 1 by S substrate. Right, once you plot against it, the biasness is somehow reduced because it evenly extrapolates. It's even out. It is starting with Vmax, right? Rather than ending with it. So somehow it is even out and it is used for kinetic studies. Okay. So what is the slope? Right? Minus Km. What is your intercept? Vmax. Vmax being the intercept. So that's important. Now henceforth, this is one of the most preferred for calculating Vmax because we try to reduce the substrate, like the dependency on substrate as possible. We are trying to reduce it. So let's see. Okay, so it's in the reciprocal form. I'll multiply with the substrate also. Not an issue here, right? So it would be S by V naught equals to Km by Vmax plus 1 by Vmax S. See, I'm doing it in simple way so that in case of your MCQs, if you forget, so you just know that this is how we reciprocated or somehow we did that. If in case you are not able to remember what is the intercept or something. So I find it easier this way. Right. Now let's see. So this is your X, this is your M positive. Yeah, you take it here as V naught, considering V naught to be 0. Now, yeah, in most of these. Now here, if I talk about this is your intercept. Okay, now this is preferred for maximum velocity. Because this S is independent, it's not depending upon something. So it's very good in terms of determining. Now the next thing that I have to come with is last time we talked about free energy change, right? So in equilibrium condition, there's an equation like this. So let's say it is activation energy. I think this won't be an issue for us, right? Now assume this is going from E star. Okay, so every molecule has its own vibrational energy. This is Boltzmann constant. This is Planck. This is temperature. Right? Now see what I'll be doing. Not an issue. Now I would do is not an issue. Not an issue. Now let's remove this ln. I guess there is no issue in this. Now would be equal to V into A. Right. As per our last studies, as per chemical kinetics, if I say. So this is what you get. And if you want to find this K, then simply just remove the A because you don't need the concentration in this case. Right. So the rate constant, first order rate constant, is given by this. The important thing is that if this K is reduced, then this exponentially it increases. So your activation energy increases exponentially. So that's important thing to remember. Now, this, when we talk about this, is the vibrational frequency, if I talk about. So it's important that your diffusion barrier can never increase that frequency of molecules colliding in the solution, right? It can be increased and it has to be somehow compensated. Now, the other thing we also discussed was Vmax, Kcat, enzyme total. In our last thing, or we refer it as K2, right? So it's the rate limiting step, the slowest in all, and it is also called as turnover number, right? So important thing here is that it's the rate limiting step. It determines the better the Kcat is, the better your efficiency is. Now let's come with Km. What was Km as you remember? K minus 1, K2 by K1. So supposedly K minus 1 is greater than K2, what will happen? Km will be equal to K minus 1 by this. Right. So it's very similar to dissociation. Right. Like goes like this. So it's dissociation. So if your dissociation is very high, then your binding is weak. And if your binding is weak, therefore your efficiency will be low. So that is Kcat by Km, efficiency ratio. And you can see that it is inversely proportional to 1 by Km, high efficiency, fast turnover, tight binding. But if Km is high, if Km is high, then there is slow turnover as well as there is, if Km is high, then there is weak binding. So let's not go into that. Okay. The characteristics of enzyme, highly specific, precise molecular substrates are required with exact geometric complementarity. There are two models, we also discussed that. There is structural persistence, so that it can be indefinitely reused, right? Once your enzyme product is formed, it is liberated like this. So your enzyme structure is not anyhow deformed, it's maintained, and therefore you can reuse velocity acceleration, right? right? The Kcat, better, best, energy reduction, better, but somehow related. Proteinaceous nature, generally proteinaceous nature. Now let's see the stability wise. So we know this reaction. Now we know this temperature thing is like it's protein, right? So even if you increase your pH, even if you increase your temperature, there is a chance for it to denature or change in the chemical structure, right? So this change, this pH protein change. So the curve is very similar, right? Even if your pH is low, even your pH is high, you will see in low pH, what is it? Acidic condition, right? Excessive H plus ion, low H plus ions. So they can be proteinated, they can be deproteinated, and that can cause structural changes. Next is how enzymes bind with the physical complementarity. Very simple model. One is Emil Fisher's and then Koshlin's. So it's very simple lock and key. Like suppose this is your lock, this is your key. This place is fixed, right? So this structure is fixed. This will come, this will bind, right? No other thing can come and bind. So there is specific. So this tremendous complementary shape which are very specific and they are already existing. It's a static model. But in Koshland, so what happens is, oh my God, you can see the substrate. I cannot bind. But here, the difference. But what I will do, upon binding, there would be conformational changes and I can bind. So there is an enzyme flexibility, alignment of the active site, structural alignment. Now, the other thing is that you may need some cofactors, right? You may need some coenzymes for inactive epozyme in order to make a functional holozyme. For example, if I talk about DNA, it needs magnesium plus 2. Otherwise, it won't function. DNA polymerase, right? Now, why? Right, for orienting the reaction, for mediating redox conditions, for statistically stabilizing or shielding negative charges. Okay, so the next thing that we need to discuss the classes. So EC3, that is class hydrolase, cleaving the water bonds. First oxidoreductase via this HO atom. Then there is transferase, transfer of functional groups like phosphatases, lyase, breaking the double bond, right? Ligases, isomerases. Isomerase is structural rearrangement. Glucose to fructose sort of thing. Ligases joining the molecules using ATP. Translocases doing nothing, just it's like a passage, acting as a passage. Let the molecules flow through me. So that is something. So thank you for joining. Let's wait for part 3 coming soon.